that modulus work we've had. So as I say, it's a real pleasure to speak here today. So I'm going to this is almost going to be kind of a survey of some older and maybe a little bit of newer work on the moduli space of Higgs bundles. So I realized that I made a mistake in my title. Of course, Nigel's name is attached to many moduli spaces, so I should have been more precise. But here I'm really talking about the moduli space of Higgs bundles. So let me just set the notation. So X will be a compact Riemann surface, and G is G bigger than 2. And so here I really do mean the original moduli space in Nigel's very seminal paper in 1987 on Higgs bundles. So I guess strictly speaking, he considered sort of a twisted version of this, but I'm really talking about, that's not going to be important. This is really moduli space of rank 2 fixed trivial determinant Higgs bundles on S. So so the first thing that one learns in this theory is the nonabelian Hodge correspondence of Hitchin, Simpson, and Donaldson and Corlett that relates the moduli space of Higgs bundles to 2 other spaces. One is the round moduli space of holomorphic connections, and then which are flat in the case of a Riemann surface. And so by taking monodrome, that gives a homeomorphism with the Betti moduli space of representation of SL2C. And this correspondence, of course, is mediated through another space, which I'll call NH, which is the solutions to the equations that appeared in Nigel's paper, and which he called the self-duality equations. So these involve an SU2 connection on a trivial vector bundle on the Riemann surface, and what's now known as a Higgs field, so an endomorphism twisted by the canonical bundle that's holomorphic with respect to the holomorphic structure induced by the connection. Okay, so so these are the characters, and so all of these 3 avatars, if you like, of the same space are sort of non-compact in their own way. And so first of all, the original Higgs bundle moduli space is, one way to think of it is kind of a completion of a cotangent bundle to the moduli space of stable bundles on the Riemann surface. And so that's sort of non-compact because one has, as we'll see, the C star action goes off to infinity. The Betti moduli space, the character variety, is naturally affine, so that's really not compact as well. And just to make a definition here, so this is the quotient in the GIT sense of the representations of fundamental group in SL2C. And finally, the moduli space of solutions to Hitchin's equations is non-compact. Maybe that's a little bit more mysterious, but it's because of kind of a PDE reason is that there's no a priori bound on what the Higgs, in any norm that you like, there's no a priori bound on the Higgs field. Okay, so roughly speaking, the aim of my talk is to kind of say something about a comparison of the ideal points. And I have to define what I mean by that, but the ideal points in each of these different kind of manifestations in the same space. And of course, there's been a lot of work already in this area, especially not just for this moduli space, but in higher rank where things are much more complicated. I'm not going to say anything. But it's something that a lot of people have worked on, and I really apologize if I'm leaving people out who are in the audience right now or watching on Zoom. But I just listed a few names here. Other work. Okay, so so let me just remind you. I think that it's been run to a lot of people in this room, not everybody. Some important features of the moduli space of Higgs bundles. One salient fact is the Hitchin map, which is obtained just by taking, in this case, just the determinant of the Higgs field. That's something that exists on at the moduli space level, and it returns a holomorphic quadratic differential in one surface force. And the striking thing is that this map is actually proper. So even though the moduli space itself is not compact, the fibers of this map are, and we'll be interested in what those fibers are. I will describe them in a second. So that's one important property. And then a second really key property is the C-star action. As I mentioned, we can think of moduli of Higgs bundles as some sort of completion of the cotangent bundle, which itself has a natural C-star action, and that C-star action persists to the completion that we were talking about, the moduli of Higgs bundles. And just in terms of the actual Higgs bundle itself, it's very simple to describe. It's just multiplication. Okay, so basically these two facts, as far as it seems to me, these two facts alone already pretty much already give you a natural compactification of the overall moduli space. So this is something that I'm not exactly sure who did this first and in what generality, but certainly it is a feature of Thomas Hausel's thesis and Carlos Simpson as well. Then Mark de Cataldo and more recently a student of mine, Wei Fan, sort of in the analytic category, proved that you have a well-defined compactification, and not only that, but it's really very, very concrete. The ideal points that you have are exactly the C-star orbits of points outside of the domain moduli space. Those appear as the ideal points. And not only that, but this has a lot of structure. It actually is a normal projective. Okay, so just as a little bit of not really a warning, but to simplify things, I may just refer to rays inside of the moduli space, and we'll see why I want to do this in a second. But so by array here, I mean the pre-image of a ray inside of the quadratic differential. So I choose a non-zero quadratic differential, and I look at in the Hitchin base at what's happening, and I consider all of those points that lie under the Hitchin. So let me just call that M below Q. All right. So let me just say a few more words about what the fibers look like. Again, I apologize. A lot of people here are very familiar with this, but it's going to be really important for the talk. So let me just remind you. So the quadratic differential gives rise to what's called a spectral curve. So solutions inside of the total space of the canonical bundle, using the quadratic differential, using the point of the Hitchin base to define this curve, which is going to be a branch cover, a double branch cover over the original Riemann surface X. And the case that I'm going to be interested in really is, we do consider more general situations, but let's just, for the sake of this talk, consider the case where Q is not a square of an abelian differential. So in that case, the spectral curve is reduced to a reduced. And it's smooth if and only if Q has simple zeros. So I'm going to be considering both cases, where first the smooth case, and then hopefully by the end of the talk, I'll say something about the case where it's not smooth, which is much more complicated. Okay, so another thing that is important is that in this case, the spectral curve has an involution, which realizes it as a double branch cover of the Riemann surface. And the fiber of the Hitchin map, all those Higgs bundles, where the determinant of the Higgs field is Q, can be described by what's called spectral data. And spectral data is some object on the spectral curve. And it's most easily described in the case where Q has simple zeros, and the spectral curve is actually smooth. And the spectral data is the choice of a line bundle on the spectral curve. So I'm not going to go through this whole construction, but this is called the VNR construction of the Higgs bundle from the line bundle on the spectral curve. And since we're dealing with SL2C, there is some fixed determinant condition, and so that line bundle is required to lie. It's called the prim variety of the spectral curve. more generally, and this is a familiar thing that we see in whenever we're dealing with moduli spaces of bundles, is that to compactify things, normally it's a good idea to go to Gaussian-free sheaves. And so in this context, the generalization for the types of spectral curves I'm considering here, the irreducible and reduced ones, then we want to compactify them from the regular Gaussian-free sheaves. Okay, so I'll say a lot more about this later on. Okay, so let me just reformulate that problem. So the problem is, so here, that's why I wanted to look at rays, for example, because then the spectral data is constant. The ideal points in the low moduli space are exactly the C-star orbits. So I can think of the spectral data as being constant, and then I want to ask the question for the given spectral data, as I go out along a ray, how does that affect, under nonabelian and Hodge, how does that affect the image, either in terms of solutions to the Hitchin equations or via nonabelian and Hodge in terms of the monodromy and the associated flat dimensions? How do those depend on the spectrum? So that's sort of a reformulation of the problem. Okay. So, yes.
Well, sister action doesn't it?
Sorry?
Doesn't it move under sister action?
So I'm just taking T to be real right now. Looking over the array, I agree with compactification I'm dividing by the full C-star. So the spectral curve is expanded, but it's just a dilation of the spectral curves in the spectral data. There's a naturalizable. All right. So let me do this slowly. As I said, I'm going to be kind of surveying some older results as well. But certainly the first case to look at here is the Hitchin section. So there's a section, of course, of the modular space of Higgs bundles, which assigns a particular Higgs bundle to each choice of quadratic differential. Actually, in this case, there are several sections, but let's not worry about that. And so even in the original paper of Nigel, there was a discussion of this, and the image of the Hitchin section for a given quadratic differential is a harmonic maps array in time space. So the points in the image of the Hitchin section can be regarded as points in typomorph space. So they correspond to, strictly speaking, they correspond to hyperbolic metrics. The origin being the uniformization of the original base of the Riemann surface. And the way that nonabelian Hodge works is via harmonic maps. And so associated to any other hyperbolic surface, one constructs a harmonic diffeomorphism between those two surfaces, and you can realize this quadratic differential in terms of the Hopf differential of that harmonic map. So this is what's called a harmonic maps array in typomorph space. So you should think of this as some sort of a array inside of typomorph space. And also associated to the quadratic differential is actually a pair of geodesic laminations, measured geodesic laminations, which can be gotten by looking at the foliation structure of the quadratic differential away from its zeros. On the other hand, of course, famously, Thurston compactified typomorph space by looking at the length functions that are associated to measured geodesic laminations. If you have a measured geodesic lamination, that gives you a way of recording lengths of simple closed curves on the surfaces and these types of length functions are exactly the ones that appear in the boundary of typomorph space. And so an old theorem of Mike Wolf's, his thesis actually, is that under the so I'm going to rephrase it in a way that he didn't do it, but let's phrase it in this way. Under the nonabelian Hodge correspondence, the image of the array associated to a fixed quadratic differential via the Hitchin section converges as T inside of type-Moore space, which I think of as a subset of the Betti modular space. These are the discrete faithful PSL2R representations or SL2R representation. That converges exactly in Thurston set to the measured dimension associated with that dimension. Okay, so this is the kind of emblematic theorem that we'd like to generalize. In some sense, the spectral data here is being specified by the Hitchin section, and now we understand how that behaves inside of the Betti moduli space. Okay, so
there's compactification. Is there any type of base point?
Sorry?
Is there any type of base point chosen in type space to define it?
To define the Thurston compactification, no. That's what's a little bit remarkable about this, because here we did choose a base point to define this, but nevertheless, when we look at what happens inside the Betti modular space, it still converges to the Thurston boundary. So in other words, in terms of compactifying type-Moore space, by using these rays, it looks like that should become on the choice of base point. In fact, it doesn't. So this gives you a mapping class group invariant way of classifying.
So I guess here the compactification is by a smooth ball, whereas the Thurston boundary is only piecewise.
Yeah.
So it's a PL boundary. So it's only its PL structure that's natural.
Right.
And independent of the base.
All right, so there's kind of a generalization of this to arbitrary sequences in the Dolbeau modular space, not necessarily along the Hitchin section, in other words. So let me just review this a little bit. So as I mentioned, the way that nonabelian Hodge works is via harmonic maps, or more precisely equivariant harmonic maps, equivariant for the fundamental group action on H2, so I'm thinking of X as being uniformized, and then via the representation in H3. So in this context, and actually a much more general context, when the quadratic differentials, or the Hopf differentials of these harmonic maps diverge, that means that their norm is going to infinity, some norm, any norm you like on the quadratic differentials, that means that the energy of the harmonic map is diverging. And what one can do is rescale the target manifold and look at some sort of a Gromov-Hausdorff limit. And so in this case, for SL2 Higgs bundles, we have the target is actually a hyperbolic space, and so as we rescale the metric to get finite energy maps, the curvature is going to minus infinity, and the Gromov-Hausdorff limit is a metric space. It's actually a tree structure. It's actually an R tree. And in this level of generality, this construction is due to Morgan-Shalen. In the case of, but it generalizes the case of discrete faithful representations, which was already done by Espina and Nicolas. So on the other hand, there's a compactification of the Betti moduli space that comes from isometric actions on the trees due to Morgan-Shalen. And let me just say a little bit about this. So this is a generalization of the Bass-Serre theory of actions on trees. But here the focus is really on length functions. So one looks at length functions. In this case, one can take, for example, the traces of the representation along a finite big collection of loops, elements of the homotopy group in X. One can look at those traces. If the representation is leaving every compact set in the moduli space, that means those traces are divergent. At least some of those traces are divergent. And so one can rescale those traces to get a well-defined limit. And part of the difficulty of Morgan-Shalen is to prove that the length function that results is a length function for an action on an R tree. So, so this is the other way of thinking of compactifying, of constructing ideal points on the Betti side. And so we generalized Wolff's theorem with George, who's in the audience here, actually, and in this context. So the Morgan-Shalen limit actually coincides with the Morgan-Shalen limit. And you can say a little bit more in the case where the limiting quadratic differential has only simple zeros. Then the limit is the dual tree to the lamination that I was talking about in the previous slide. There is a subtlety here about saddle connections and something called folding of trees, and I'll come back to this in a few minutes. Okay, so this is kind of a generalization on the Betti side. But you'll notice that you're losing, obviously, with this kind of construction, you're losing a lot of information because all you see in the limit is, roughly speaking, something that corresponds to the quadratic differential. And you're losing all of this vector. So that's kind of a mystery. So let me come back to that mystery in a little bit. Okay, so I want to switch gears now and go to the solutions to the self-duality equations. So what do asymptotics look like there? So here I just rewrite the solutions to these equations again. So for a Higgs bundle, then we say that there are solutions if they satisfy these two equations. And you'll notice that there's a simple way to find a solution, and that's to make each of these terms themselves individually zero. So why not just look at a flat connection and a Higgs field that commutes with its dual? Okay. So, well, if you think about it for a few minutes, you'll see that somehow there are topological obstructions to actually doing that. And so, but nevertheless, we can attempt to do this, let's say, off of a finite set. So here's a definition, which I believe in this formulation is probably leaving Mochizuki. So a limiting configuration is a solution to these decoupled equations. So a smooth SU2 connection, flat SU2 connection, and a Higgs field, a holomorphic endomorphism that commutes with this dual. But we only require this off of some finite set. And moreover, we need a little bit of regularity to really say that we're saying something about an object on the completion on X itself. And it suffices to just assume that the norm of the Higgs field extends continuously. And just let's redefine Z then to be exactly the zero set of this guy. Okay, so this is what we mean by limiting configurations. And in this case, because of this continuous extension, then it's not hard to see that the quadratic differential, which is defined C, actually has removable singularities. So this gives us a well-defined holomorphic quadratic differential. And here's a theorem. So this is first due to Taubes in, again, more generality than the way I'm phrasing it here. It was reformulated by Mochizuki, who proved it again in more generality than I'm phrasing here, and also Sichi. So there's been quite a bit of work on this, but I'm sort of looking at the most simple case of this. And the statement is the following. So if you have a sequence in the solutions to the self-duality equations, then either converges inside of the modular space, which means up to H, or it diverges. And if it diverges, we can track the zeros of the quadratic differential, and that will limit to some quadratic differential, which has a finite set Z of zeros. And then after rescaling Higgs fields, then they converge away from Z. And not only that, that's maybe not surprising. The surprising part is this fact that phi is getting very, very close to a Higgs field that commutes with its dual in such a way that, in fact, the curvature stays bounded. And once the curvature stays bounded, you have a little bit of compactness, and you get convergence of the connections as well. So this is so here I've just phrased it as it converges. In fact, it converges as locally smoothly away from Z to a limiting configuration. Okay, so So if you work a little bit harder, you can use limiting configurations that they themselves form a compact set. And so you can use limiting configurations to define a compactification of the solution space, define a compactification of the solution space, which is a nice Hausdorff space. And the ideal forms of limiting configurations. Okay. So now let me tell you what I can say about these things. So let's start with the case of the smooth spectral curve. So again, that's the situation where Q has simple zeros, and as I said, the fiber of the Hitchin map in this case, the prim variety. So some generalization of the Jacobian where we take into account the involution. And it turns out that limiting configurations of the type that I was writing down in the previous slide, the Higgs field itself is determined by the quadratic differential. The connection is the free parameter there, and the possible connections that appear can also be identified with prim differentials. So just one forms that are odd with respect to the action of the involution. And modulo a lattice, the gauge equivalence introduces a lattice there. And so prim differentials modulo this lattice is natural way isomorphic to the prim variety. And so an alternative way of thinking of this is that this connection for the limiting configuration, it's an abelian connection. It's a connection on a line bundle. And I can think of the full abelian, full SU2 connection, which has a reduction to U1. I can think of that full abelian connection in SU2 as being the push forward under the branch double cover map of this abelian connection on the spectral curve. And on the spectral curve, it's naturally the Chern connection for a line bundle with a choice of weights at various points. So these are sometimes called parabolic line bundles. So they have singular Hermitian structures, so the connection degenerates at these points. But it's a very explicit sort of description, where of course the line bundle is the spectral data in this case. And importantly, this is maybe a technical point, which is not really clear why it matters so much here, but importantly, the weights of that parabolic structure are all the same at every point for -1/2. But let's say there's just some fixed number that is prescribed. Okay, so the theorem is that of Matteo Svoboda-Weiss-Witt is that you can reverse this process. So starting with the limiting configuration type of this just described, we can really realize it as a limit of Higgs bundles. And so this really gives a homeomorphism between the two compactifications here, at least along the locus where the quadratic dimensions have simple zeros. Okay, so this is a rather strong comparison of the partial compactifications of these two spaces. Okay, so let me go back to the Betti picture for just a moment, and I want to stay in the context of simple zeros because the Matteo Svoboda-Weiss-Witt theorem actually will tell us something in this case as well. So here I want to introduce some sort of topological notions that are quite removed, apparently, from the notion of the Higgs bundle. So let me go back to the lamination that we were talking about for one of the foliations of the quadratic differential. And I'm sure I'm going to get vertical and horizontal mixed up, so don't take this seriously. It's one of the two laminations associated with the quadratic differential. So then an idea of Bonohan's associates what are called shearing or bending cocycles to this lamination. So so here the shearing part is the one with real coefficients, and the bending part is the one with circle value coefficients. And let me just maybe I should just say something in words here about what's going on. So the origin of this idea is the following. So we're interested in the lamination. We think of as giving us this maximal. I didn't explain what maximal means. It means that the complementary regions are triangles. And so we wanted to form a hyperbolic structure, thinking of the hyperbolic structure as being gluing a bunch of hyperbolic triangles together. So hyperbolic triangle, there's only one, right? There's only one up to isometry, one hyperbolic triangle, which I can draw on the hyperbolic plane. This thing. One of the vertices is at infinity, and I put the other two here. Okay, so up to isometry, there's only one of these two guys. But of course, if I have two of them and I want them to be adjacent, then there's a modular parameter. And so this modular parameter is I can think of it as at this point x here. That's one way to think of that choice. This. Another way to think of that choice is, let's see, it's one way to do it. I can take the geodesic that goes from this one here to this one. And I can draw the corresponding geodesic this one. And there's a gap, which also gives us a number, and I can associate a sign to that number. Let's say that it's negative, that it's always to the left. And you can see that that doesn't matter which way you're coming between the two ideal triangles. So there's a well-defined sign distance that occurs when we put two ideal triangles together, and that's what's called the shearing. So this is the shearing. And then if I want to think, so this is a picture inside of H2, but if I want to think of the picture inside of H3, then of course there's another thing that I can do with the two ideal triangles is I can bend. Right, so I can put a crease in here. My picture is going to really degenerate here, but okay, so I think you can see what I mean. So there's some sort of an angle that I can put here, and this is supposed to be the bending. Okay, so this is motivation anyway. Now, if we actually wanted to deal with the construction of deformations with these laminations, then this picture is way too simplistic, because the lamination is this sort of thing that sort of generically the cross section of campus are very, very complicated. And so what you want to do is you want to average out the bending. So you want to take two triangles that are possibly far away and assign a total shearing to those two triangles and a total bending to those two triangles. And you'd like to have that make sense. That's where the cocycle condition comes in. So if you stick a triangle in between, you want to make sure that these total numbers add up correctly. And so there's a kind of cocycle condition that appears in the definition of these things. But the point is that these cocycles form a finite dimensional space, and in particular, the circle value ones give you a torus of, surprisingly, dimension 6G minus 6. And so the theorem of Bonahan is that there's a convex polynomial cone. This is not so important, but there's some subspace of the shearing cocycles. So the point is you can't shear too much. There's a subset of the shearing cocycles such that when I look at that subset across any possible bending cocycle, then there's a map which actually is a holomorphic map. So here I should think of this as right, the imaginary part of the bending and the real part is the shearing. This is actually a biholomorphism of the open set inside the bending. So I kind of think of this as the Betti topological version of the Hitchin fibration, because it's got the right dimension. We can think of this, we didn't really say this, but we can think of the cone itself as corresponding to, say, zero bending, and that indeed corresponds to a copy of Hyperkaehler space. And then this torus, well, is very reminiscent of the prime variety that we see in Hitchin vibration. So this is kind of in some sense, a topological avatar of the Hitchin vibration. So
And this cone structure is supposed to be like scaling your differential, the cone structure in the base. Going off to infinity, the cone along is raised.
certainly going off to infinity in the cone is one direction to going off to infinity. But why do we have the boundary of the cone? That's because if you shear too much, you won't actually get a hyperbolic surface. So imagine that I have all these ideal triangles. I have to piece them together inside of the hyperbolic disk. And if I shear too much, then it's just it's not going to work. So the boundaries of these cones are sort of there precisely because there's a bound to the amount of shear. Okay, right. So let's see. So here's a theorem. So let me just say again. So again, we sort of thought of this as kind of a version of the Hitchin vibration. We wanted to sort of see that asymptotically, it really does correspond to this torus factor, this bending factor, really does correspond to the Hitchin fiber asymptotically, and that's more or less what we proved. So this was with Lutz and myself and Mike Wolf a while back. So first of all, that torus of bending cocycles is naturally diffeomorphic to the prim variety itself. Again, this passes through prim differentials, where the bending cocycles, these angles, are essentially the periods of the prim differentials. That's how that isomorphism goes. And then the statement is, the second statement is that if I go out along a ray inside of the Dolbeau moduli space, so here again the lamination, so the Bonahon parameterization depends on the choice of lamination. So I'm choosing the lamination that corresponds to that quadratic differential. So if I go out along the ray, then eventually I'm in the image of this Bonahon map. That's script B. Let me just remind you that script B is this biapolymorphism down here, but it's only on to an open set. And so I need to know that I'm eventually in that image. And then the statement is that the spectral data, which we think of as a point of the prim variety, and the bending cocycles, which is the point in this space of bending cocycles that's identified here with the prim variety, those two things are asymptotic. So in some sense, this vibration, the fiber with this Bonahon map is matching up with the Hitchin fiber as we go to the Okay, so fine. So this is nice. Let me just come back to the this in some sense this solves the mystery of Morgan-Shalen compactification. When we rescale everything and take a Gromov-Hausdorff limit, all we see is the creases, the lamination along which we're bending, and we've forgotten the bending angles themselves, and this sort of recovers the bending angles. But it also gives you a slight refinement. So remember, I said it was an ambiguity in whether we get actually the dual tree to the quadratic differential or not, and we can actually predict when folding will happen. And the folding of the tree, of course, is related to the bending of these flats. So I just want to put that in there, but it does give you a slight refinement of the Morgan-Shalen. Okay. So let me mention another kind of application that comes out of the same analysis, and that is to look at the overs, or the complex projective structures. So these are monodromies of differential equations, second order differential equations on the Riemann surface, and they're parameterized by quadratic differentials, strictly speaking by projective connections. So let me know. So I choose a quadratic differential, and then I look at the solutions here, and I can scale. So this is sometimes called the WAB problem. And this naturally gives you a family then in any moduli space. And one natural question is, what does that correspond to under nonabelian in terms of the Higgs bundle? Can we write down the Higgs bundle corresponding to an OPER? And the answer, of course, is no. We can't. But can we say something asymptotically at least? So here, let me try to give an answer. So there's we talked about the Hitchin section before, which corresponds to a copy of type space. There's another natural choice of spectral data, which I guess maybe it's obvious to some people, but it kind of surprised me a little bit. So we have this canonical section, which is sometimes called a Seiberg-Witten differential. If you take its imaginary part, that gives you prim differential, it gives you a point in this. And so that gives you a section. It's not a holomorphic section anymore, but it is something that's distinct from the Hitchin section. And so let me just call that lambda. Okay, so it's a distinguished point in the spectral curve. And so then the theorem is the following. So of course the OPERs, if we look at the Higgs bundles that correspond to the solution to that equation at the very top, there's no reason why the image of the Hitchin map on those should have anything to do with quadratic differential. Of course, you suspect it must, but what the precise relationship is not at all clear. And again, it does turn out to be asymptotic. So the OPERs don't necessarily form a section, as far as I know, of the Hitchin vibration, but sort of asymptotically, twisting is asymptotically sort of does. And then once you know that you're close to this quadratic differential with simple zeros, it makes sense to compare spectral data. And the spectral data then is asymptotic to a certain multiple of this funny Seiberg-Witten choice of spectral data. So what's happening here, notice there's a T in front of this. So what's happening is that as you go out, you're sort of very close to being along the ray of quadratic differential, and up in the fiber, you're spinning around, spinning around, spinning. So that's it seems to be the structure of the image of complex projective structures. Again, in the case where Q has simple zeros. All right. So this is kind of a little bit of an aside. It's maybe not so relevant, but it's a reasonable thing. So now I want to talk about a singular spectrum. So I want to ask the question: what happens when we move to quadratic differentials that have zeros with multiplicity? But maybe we should ask also, which representations, first of all, correspond to. Is there something topological about representation being a smooth fiber? And the answer is basically no. Almost all representations can be realized in a smooth fiber in the Hitchin vibration for some choice of Riemann surface structure. So this is the result that also uses the techniques that go into the previous theorems that I was just mentioning. But this doesn't really say too much because this apparently is something that's not at all uniform as we go out to the boundary. So that's why I say this is sort of an aside. It may be a curiosity, but I don't think it really says anything about the structure of infinity. Okay, right. So now let's talk a little bit about singular spectral data. So when Q has zeros with multiplicity, then the spectral curve is no longer smooth, as I mentioned before. Let me just, for the sake of, we always assume that it's reduced, so we always assume that Q is not a square. Let me just keep that assumption in force here. So I'm going to assume that S is reduced and reducible. So, and let's let S tilde be the normalization of the spectral curve. So now a smooth spectral curve, and we have, again, this is going to be a branched cover of the original Riemann surface. And so we can ask, what is the spectral data in this case? And this is also something that's been studied by a lot of people. In particular, for us, anyway, there are papers of Peter Garpen and De Oliveira and Johannes Horn that really detail in quite a useful way how to think about the spectral data. So I'll come back to that in a second. So, so one idea for the construction of limiting configurations is the following. So if we take spectral data, so again, now this is a rank 1 torsion free sheaf on S, and we pull it back to S tilde and mod out by torsion so that we now have a line bundle on S tilde. We can look at parabolic structures there on that line bundle and again push them forward and try to realize those as a good definition for limiting configurations. And that's exactly what Morgan-Shalen does. So here's his theorem. So, so it's a very, very general statement. So, so if we have a family of Higgs bundles and we scale the Higgs field, say, then this has a well-defined limiting configuration. I should correct it something here. So here I'm assuming that the determinant of E is a Q from before. So not no bone columns. So this has a well-defined limiting configuration as T goes to infinity. And the connection in D can be thought of as the push forward of an abelian connection on a parabolic line bundle. And the crucial thing here is the line bundle is constructed in the way that I just described. And the crucial thing here, again, is that the weights have this kind of very, very uniform structure. On some divisor, let me not get into too many technical details right now. On some divisor, which is associated with ramification of the cover. Okay, so this is one way to think of, this is the way to think of limiting configurations for singular spectral curves. So he has, in other words, he has a very, very precise description of, so we already knew that we had limiting configurations, but he has a very precise description of the points that occur. So here, this is the mysterious part, I guess, is that it turns out that this extension, so this gives us an extension of the nonabelian Hodge correspondence between from the Dobo side to the completion of the solutions to the self-duality equations. And what we proved, so this is a recent result, is we sort of characterize when that extension is a reasonable map. So again, this is if we have zeros of only odd multiplicity in the quadratic differential, then this extension is very nice. It's a nice continuous map. And but the surprising thing is that this map goes completely crazy in general. So as soon as there's 1 0 of even multiplicity, as soon as there are nodes, in other words, in the spectral curve, then there's discontinuous behavior in the extension of this map.
Which also happens at the beginning. This rank 2 bar.
Just right. Yeah. Exactly. So yeah, I have just a couple of minutes, I guess. Let me not go into too much detail about this, but so what is the problem? So the problem is directly related to the structure of compactified Jacobians. So what is happening here? So again, we have S is the original spectral curve, and S tilde is its normalization. And the rank 1 torsion free sheaves on S is going to be a compactification of the Jacobian. You can do this as a Jacobian, you can do this for the prim variety as well. And structure of that compactification has a subtlety about it, which turns out to be very much related to the choice of these weights for the parabolic structure. So let me try to say something about that. So there's another moduli space, actually a moduli space that you can construct called the parabolic modules on S tilde, with a well-defined map to the I didn't put the the Jacobian of the normalization. And this moduli space intermediates between the compactified Jacobian of S and the Jacobian of S tilde. But the map here, tau hat, that goes from this space to the other, has a fiber precisely over the boundary points, over the non-locally free sheaves on S. And those two points in the fiber of tau don't necessarily live over the same point in the Jacobian of S. And so it turns out that there's a kind of stratification. So here I've written some things, but let me just try to say this in words rather. There's a kind of stratification of the compactified Jacobian along which the correspondence that we were talking about before, the extension, Machizuki's extension of the nonabelian Hodge correspondence is continuous. But when we jump between strata, that's where the discontinuity appears. And it's related to this fact. So what is the fiber of what I'm calling PR? What are these projected modules are, roughly speaking, pairs where we have a line bundle on S tilde. And then the fiber here is a choice of, in general, it's an element of some Grassmannian, but it's a choice of subspaces of the fiber of that line bundle over the ramification point. And what do I want to say here? So and the as that Grassmannian, as that choice of that element of the Grassmannian moves around in terms of the stratification, we get jumping behavior in the weights for the limiting configurations. This is kind of what is responsible for the discontinuity. So I think I've probably not done a very good job of explaining this last part, but this is just some idea. It would take way too long to say much more about that. So so I think I will actually stop there. And so this last part, as I say, is kind of a mystery to us. We really don't understand what the structure means, but hopefully with some more work we can say more later. Okay, thank you.